So, good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, I'm very pleased to welcome Thibault Lefeuvre, who has come all the way from Université Paris 6. Is that right?
Yeah, that's right, yeah.
Université Paris 6, Jussieu. And he will be talking to us about the marked length spectrum, geodesic stretch, and the pressure metric. Just before Thibault starts, I'd just like to remind everybody that I think it's really good when people ask questions. So please don't hesitate to ask questions. Okay, so it's now over to you, Thibault.
All right, well, thank you very much for the invitation. It's a pleasure to be here online. So as you were just saying, feel free to interrupt me. Feel free to interrupt me if you have any questions or comments or whatever. So the results that I will describe today they're based on earlier work with Colin Guillermo. So it was a paper that we published in 2018 or something, 2 years ago, I think. And then we gave a new proof of this results about the marked length spectrum using some ideas that we had in collaboration with Gerhard Knipper. So I'm going to talk about this today. All right, so here's the problem. So we consider a smooth closed manifold and we assume smooth closed Riemannian manifold, and we assume that it has a negative sectional curvature. So I will denote by capital C the set of free homotopy classes in the manifold. And there's an elementary fact of Riemannian geometry, which is that when you have a negatively curved metric, then in each free homotopy class, there is a unique periodic geodesic for your metric in this class. So, for example, if you take your, say, a genus 2 surface, you consider the set of free homotopy, the set of curves, sorry, which wrap once around the central part here, the annulus here. So this class is called C. And then what this fact says is that there's precisely one unique closed geodesic in this class. And it's here in blue. And I will denote it by gamma G of C. And of course, this geodesic highly depends on the metric that you fix on your manifold. All right, so from this, you can define what's called the marked length spectrum, which is a map going from C, so the set of free homotopy classes, to R+, and it's defined in the following way. So you take your class C and you map it to the length of the unique closed geodesic in the class little c. All right, and so the main conjecture in the field, and what is important here is that this map that I just defined, so the marked length spectrum, is invariant by the action of a natural group, which is the group of diffeomorphisms which are isotopic to the identity. Namely, if you take such a diffeomorphism and you consider phi star of G, so the pullback of the metric G by this diffeomorphism, then the two metrics G and phi star of G have the same marked length spectrum. And it's very important here that the diffeomorphism is isotopic to the identity. All right, and so the main conjecture in the field is due to Burns and Katok, and it states that the marked length spectrum should determine the metric G. So in the following sense, namely, if you take two metrics which have the same marked length spectrum, then they should be isometric. There should exist a diffeomorphism phi, which is isotopic to the identity and such that phi star of G prime is equal to the metric G. Right. So there is another reformulation of this problem, and I will come later back to this. And it has a more, say, a more dynamical flavor. It's fairly easy, and I will explain where this comes from. It's fairly easy to see that having same marked length spectrum is actually equivalent to having conjugate geodesic flows. So when you have two metrics, G and G prime, they both have geodesic flows, and the geodesic flow is a flow which lives on the unit tangent bundle of the metric. So it's not on the base manifold M, it's one floor higher on the unit tangent bundle. And as we will see, having two marked length spectrum, the same marked length spectrum is equivalent to having conjugate geodesic flows. And then the question is, does this conjugacy H comes from the base M. In other words, is there a diffeomorphism phi from M to M, from the manifold to itself, such that this conjugacy H can be written as phi, so that's for the base, and then in the velocity variable, d phi. Okay, so this dynamical point of view will be very important in my talk, and I will come back to it later. So about this problem that we call the rigidity of the Mark-Lane spectrum, there are known results, and in particular in dimension 2, the problem was solved. So it was solved in 1990 in 2 independent papers by Christopher Crook and Jean-Pierre Otal. And but they're proof. I mean, these are very beautiful and geometric proofs, but which cannot really be improved to. I mean, they heavily rely on the fact that well, in surfaces, geodesics have to intersect themselves, etc. So it's really like a 2-dimensional proof that you can really use in higher dimensions. Now, a couple of years before, Katok had a proof when the 2 metrics are conformal. So when you take G and G prime in the same conformal class, and there are other partial results due to Hammenstadt and Besson-Courtois-Gallo when one of the two Riemannian space is a locally symmetric space. Okay, so the theorem that we proved with Colin 2 years ago is a local version of the Burns and Katok conjecture. And the statement is the following. So we fix a metric of reference G0, and we assume that this metric is negatively curved. And what we proved is that there is an integer n and a small epsilon, strictly positive, such that if you look at the metrics which are epsilon close to G0 in the CN topology, and you assume that your metric G has same Mark-Lane spectrum as G0, then G is actually isometric to G0. So this is really like a local version of the conjecture. And of course, the global statement would be to, well, get rid of this epsilon here. But of course, this is really the hard part. And for the moment, it's an open question. So just a comment, actually, our methods can be improved and we don't really use negative curvature. So it can be relaxed to non-positive curvature and Anosov geodesic flow. So that's really what is important here in our techniques, the fact that the geodesic flow is a hyperbolic flow. And in particular, it's well known that in negative curvature, it's the case. Okay, so the new result that we obtained last year actually with Colin and Gerhard Knipper is the following. So it's a stability estimate for this problem, and it's not only is this a stability estimate, but it's better in the sense that it's a stability estimate which only involves the asymptotic behavior of the Mark-Lane spectrum. So what we prove is, again, there's a small neighborhood of the metric G0, such that if you pick a metric G in this small neighborhood, there exists a diffeomorphism phi, such that if you look at phi star of G minus G0, so here this has to be really understood as a distance between the isometric classes of G0 and of the metric G. So the distance between the two isometric classes is controlled by the ratio of the Mark-Lane spectrum, but when you only look at length going to plus infinity. Okay, so we only need what we call the asymptotic Mark-Lane spectrum. So here we have the lim sup and then the lim inf. All right, so this is an improvement of the first theorem, of course, but it's actually not that good. I mean, it's quite expected insofar as, well, it's something that is well known to the experts. The asymptotic behavior of the Mark-Lane spectrum actually completely determines the behavior of the whole Mark-Lane spectrum. So for instance, if you assume that when you take the ratio of the length, if you assume that the asymptotic Mark-Lane spectrum are the same, namely that, that these limits are equal to 1, then it's fairly easy to see that actually all the Mark-Lane spectrum is the same, precisely because, well, you can just take, like for instance, you fix a geodesic and you just take iterates of these geodesics. So these are no longer primitive geodesics, but it doesn't matter. And then you see that it's fairly easy to see that the asymptotic behavior of the Mark-Lane spectrum completely determines the whole sequence. So the real improvement does not really lie in the exact result, but it lies in the stability estimate that is here. And that's what I'm going to try to explain today.
Sorry, can I just ask, is that really
sure.
h? Is that really h minus half on the left-hand side?
Yes.
So it's quite weak.
Yes, it is. So it's extremely weak, but as you can see, we always make this assumption, which means that you can always interpolate. If you want a better norm here, you can always interpolate h minus 1/2 with this space of high regularity, and you're gonna get you're gonna lose some power here, so you're not gonna get 1/2. You're gonna get maybe a quarter or something like this. But you can always improve this by interpolating with a higher spaces of higher regularity.
Exactly, of course. That's what I was talking about, Sebastian. Thank you, Thibault.
All right.
Yes,
so what
remember.
about? So what about the technique? So to be very quick, so I'm going to talk about Anosov dynamical systems and the link between Riemannian geometry and also polyreal resonances. So I will recall everything, and everything is sort of I mean the central thing here, the central theory is really microlocal analysis. So even though I will not really do microlocal analysis, it's somehow everywhere in what I'm going to say. And in the end, and that's really what we found in this new paper with Colin and Gerard. There are some interesting and somehow unexpected link with the Teichmüller theory, and I hope that I will have enough time to talk about this link here in the end. All right, so geodesic stretch. So what is the geodesic stretch? And that's really the central notion that will allow us to prove both theorems, theorem A and theorem B. Okay, so we fix a metric of reference G0 with negative curvature, and we take metrics which are close to G0. And I will denote by X of G the geodesic vector fields of the matrix. Now, by Anosov structure, when you have metrics with negative curvature, I recall that the geodesic flows are Anosov, so they are really hyperbolic. If you don't know what is the Anosov property, I will explain this in 2 or 3 slides, I think. So what is important is that when you have 2 Anosov flows, they are connected by what's called structural stability. In other words, there is a map H going from the first unit tangent bundle to the second unit tangent bundle, and which maps, so the differential of this map H maps the first geodesic flow, not exactly on the second geodesic flow, but on a function times the second geodesic flow. So here the function AG, it's called the infinitesimal stretch, and it's a sort of time reparametrization which tells you how to pass from one geodesic flow to another when they are close. Now, what is why do we introduce this function? Well, precisely because it has a very strong relation with the Mark-Lane spectrum. This function AG, the infinitesimal stretch, allows us to express the Mark-Lane spectrum of the metric G, which is close to G0. Now, how do we do this? Well, let us fix a free homotopy class, for instance. So we have the closed geodesic in this class C for the metric G0. And now if we perturb the metric G0, then this geodesic is going to be moved. And here, the red geodesic is the gamma G of C, so the geodesic in the class C, but for the metric G. And now the length of this closed geodesic is precisely given by the integral of AG along this blue geodesic, which was the original geodesic for my metric of reference G0. Now, what you can see from this is that if the 2 metrics have the same Mark-Lane spectrum, namely LG is equal to LG0, then this means that the function AG minus 1 integrates to 0 along all closed geodesics. And now this, oops, there's a problem here. And now this here, when you have a function that integrates to 0 along all closed geodesic, this immediately implies by a theorem that is due to Lifshitz that AG minus 1 is cohomologous to 0, which means that there exists a function U such that AG minus 1 is a derivative in the direction of of the geodesic vector field x g0. Okay, and this here is exactly equivalent to saying that, so that's a very elementary exercise, that's equivalent to saying that the two geodesic flows are conjugate. Okay, so just to have this picture in mind, here the conjugacy H, you can really picture easily what's going on when you go to the universal cover and you lift your two geodesics. Namely, that's my blue geodesic for G0, that's the red geodesic for G, and the map H, so the conjugacy, it's an orbit conjugacy, it's so the universal cover, it has a boundary at infinity, which is represented here by my disk. And the map H, it sends this blue geodesic to the red one, and the two geodesics have the same endpoints on the boundary at infinity. Okay, so that's really the picture to have in mind about this map H. All right, so now what is the definition of the geodesic stretch? Well, the geodesic stretch of the metric G, so that's a functional, it takes a metric and it gives you back a number. It's nothing but the integral of AG, of the infinitesimal stretch, with respect to the Liouville measure of the first metric, G0. And what we're going to do, and that's really the main claim of my talk, is we're going to show that the geodesic stretch is a strictly convex functional on the moduli space of isometry classes. And that's, so I will explain all the words in details here, but that's really the main claim, and that's where, that's the thing on which everything relies. So I'm cheating a bit when I'm saying this because at some point we have to restrict to a hypersurface in the space of all metrics. So, I mean, this is only a technical point. So I don't want to give too many details about this, but roughly speaking, we're going to restrict to a hypersurface, which is given by f of g is equal to 0. So that's a level set of a function. And f of g, so I will give the precise definition for this f of g, but for the moment you can think of f of g as the function which maps a metric to its volume or something like this. It's really, what's important is that the derivative of f is equal to the derivative of the volume at g is equal to g0. Okay. So that's only technical.
Thibault,
yeah.
Thibault, there is a Graham wants to know if you can define what is the Liouville measure.
Oh, the Liouville measure. Yeah, sorry. So when you have the unitangent bundle, there is a canonical measure, which is how can I put this? The Liouville measure, if you want. So the unitangent bundle is a sphere bundle over the base manifold M, and if you want the Liouville measure in local coordinates, it would be the measure on the base M times the Euclidean measure in the sphere. Okay, so I mean that's really that's the smooth measure that is preserved by the geodesic flow. That's a natural measure on the unitangent bundle. All right. So I will take some time to explain what I mean here by this claim, and then we will prove this claim. So first of all, I need to explain what is the moduli space of isometry classes. Okay, so for that, I need to talk about the local geometry of the space of all metrics around the metric, our metric of reference G0. Okay, so we fix our metric G0 here, which is in the center of your screen, and passing through G0, there is the orbit of G0 under the action of the group of diffeomorphism. So that's here, what is in black here. So I will denote this orbit by big O of G0, and it's all the phi star of G0 when phi is a diffeomorphism that is isotopic to the identity. Now, the tangent plane to this orbit is in red, and it's precisely equal to all the Lie derivatives of the metric G0. So it's all the symmetric two tensors which are of the form LV of G0. So Lie derivative in the direction V, where V is a vector field, of the metric G0. And these symmetric two tensors are called potential tensors. Now, there's an orthogonal space to this red space, which is in blue here. And it's called the set of solenoidal tensors, and these are all the tensors which are in the kernel of a certain divergence type operator. So I will not define this operator delta, but It's not very important. What is important is that these two spaces are orthogonal for a certain natural L2 scalar product. And what is more important even is that this blue space is actually transverse to all the orbits of the matrix under the action of the group of diffeomorphisms, namely the blue space, but it's also the case for all the orbits in a neighborhood of G0. So in other words, if you take a metric G in a neighborhood of G0, then you're always going to be able to find a first diffeomorphism phi such that phi star of G belongs to this blue space of solenoidal tensors. Now, what this says is that the set of solenoidal tensors is a local representation for the moduli space of isometry classes around G0. So if you want, it's a local chart for the moduli space of isometry classes. All right, so just another comment. If you take a tensor F, a symmetric to tensor F, you can see it actually as a tangent vector to the space of all metric at the point G0. Okay, so you can really, a symmetric to tensor can really be seen as a tangent vector at G0. And the fact that these two spaces, the blue one and the red one, are orthogonal, precisely tells you that your symmetric to tensor F admits a unique decomposition in the form LV of G0 plus H, where LV of G0 is the potential part, so the part that belongs to the red vector space here, and H is the solenoidal part, and it belongs to the blue space there. Okay, so remember, the main claim was that the geodesic stretch functional was strictly convex on the set of solenoidal on the moduli space of isometry classes. Now, using this picture, what does it mean exactly? Well, it means that if we restrict the geodesic stretch functional to this blue space of solenoidal tensor, it is now sufficient to prove that this functional is strictly convex in restriction to this blue space. So in other words, I'm trying to prove this. I'm trying to prove that the geodesic stretch I of G looks like this in a neighborhood of G0 when I look at it above the set of solenoidal tensors. Okay? So I need to prove that the first derivative of the stretch is 0 and that the second derivative is strictly convex. All right, so let's start. That's where it starts to get a bit painful. We have to compute things. So we start looking at the derivatives. So the 0th derivative, I mean, this is just the value of the stretch at G0. So we just evaluate this, but it does not really matter. So it's the integral of A G0 with respect to the Liouville measure. Now the infinitesimal stretch of G0, so that's the metric, but with respect to itself, so it's always equal to 1. And so that's actually equal to the volume of the unit tangent bundle. And without loss of generality, we can always assume that it's normalized and equal to 1. Okay, so now I want to compute the first derivative of the stretch with respect to the metric at the point G0, and I'm trying to prove that this derivative is equal to 0. Okay, so for that, I need a preliminary computation. So recall that when I fix a free homotopy class C, I have my G0 geodesic, and then nearby I have my G geodesic, which is in red here. Now recall that the red geodesic, its length can be written in terms of AG. So the length LG of C is equal to the integral of AG along the blue geodesic, but it's also equal, so that's the usual definition of Riemannian geometry. It's equal to the integral of the tensor G to the power 1/2 along the red geodesic itself. So I have two different expressions for the length of this red geodesic. Now, if I differentiate with respect to the metric and evaluate at the point G is equal to G0, well, I have two different expressions for this differential. On the left-hand side, I have nothing but this expression. Okay, so the integral of the differential of A at the point G0 in the direction H. So H here is a symmetric to tensor. And then I have on the right-hand side the derivative of this. Now, this is an integral which depends on the curve, and the curve depends itself on the metric. So there are two terms in the derivative. But using the fact that geodesics are minimizers of the length among free homotopy classes, you can easily check that the dependence on the metric here actually does not matter. It does not appear in the computation. So you only get the derivative involving the tensor here. So that's what you get in the end. You get 1/2 of the integral along the G0 geodesic of the tensor H. Now, what does it mean to integrate a tensor along a geodesic? Well, there's a way to see this, which I particularly like, which is you pull back your tensor on the unit tangent bundle. Namely, when you have a symmetric two tensor, you can define a canonical function associated to this tensor, which lives on the unit tangent bundle. And this function I will denote it by pi2 star of h. So the 2 is for symmetric two tensors. And how is it defined? Well, you evaluate it at the point x and the direction v, and it's given by the symmetric tensor h that you evaluate at the point x, and then you plug twice the speed vector v. Okay, and it's a symmetric two tensor, so this is not going to be 0. Well, it can be 0, but I mean, not always. And then this integral is simply defined as the integral of pi2 star of h, and then here you evaluate at well, you go through. So that's a periodic orbit for the geodesic flow of G0. So you just integrate along this periodic orbit of the geodesic flow of G0. Okay, so what does this computation tells us? Well, if you pass this term on the left-hand side, you get that this function here, which lives on the unit tangent bundle of G0, integrates to 0 along all closed geodesics. Now, as I said before, by Lifshitz theorem, this implies that this function is a co-boundary. Namely, it's a derivative in the flow direction of the flow direction of the geodesic flow of G0. Sorry. So you can really write this as this difference of two functions. You can really write it as x of u, where x is the geodesic flow of G0. Okay. Now, once we have this computation, we can compute the first derivative of the stretch. So the first derivative of the stretch is, so recall that the stretch is just the integral of the function ag. So if I differentiate, I get the integral of the derivative, so I get this. And now I know that this is equal to pi2 star, so 1/2 of pi2 star of h plus a co-boundary. Now when you integrate over the whole manifold a co-boundary, then this is always equal to 0. And this comes from the fact that the geodesic flow of G0 preserves the Liouville measure here. So that's always equal to 0. And I'm left with 1/2 of the integral of pi2 star of h with respect to the Liouville measure of G0. And now you can also check that this is precisely equal to 1/2 of the derivative of the volume of the unit tangent bundle with respect to the metric. And by our normalization assumption, by the fact that we're restricting ourselves to a hypersurface f of g is equal to 0, this is going to be equal to 0. All right, so that's a bit painful, but that's the computation for the first derivative. It shows that the stretch, the geodesic stretch, has a critical point at G0. All right, so we have to compute the second derivative of the stretch. And that's going to get a bit more technical. Now I need to describe exactly what is this hypersurface to which we restrict ourselves. All right, so this functional f, which, so I said before that it was the volume, but I was actually cheating a bit. It's not exactly the volume. So it's a functional going from the set of all metrics to R, and it's defined as the pressure, the topological pressure of a certain potential, which is Holder continuous. And this potential is minus the unstable Jacobian plus Ag minus 1. Okay. So if you don't remember the definition, the topological pressure is defined, it's a notion from dynamical systems. It's the supremum over all ergodic and invariant measure of the metric entropy of the flow plus the integral of the potential with respect to the measure. Okay, but it doesn't really matter. What is important here in this problem is that because we're interested in the rigidity of the Markland spectrum. So what is important here is that if we take two metrics with the same Markland spectrum, namely LG is equal to LG0, then we saw before that this means that AG minus 1, so the infinitesimal stretch minus 1, is cohomologous to 0. Namely, it's equal to a coboundary XU. And then if you plug this in the expression for F, you see that F of G is then the pressure of the unstable Jacobian plus a coboundary. And the pressure here does not see coboundaries. So it's equal to the pressure of the unstable Jacobian. So it's equal to 0, which means, in other words, that the hypersurface to which I restrict my problem, Fg is equal to 0, always contains all the matrix G which have the same Markland spectrum as G0. So that's important for my problem, because if I was starting to exclude the metrics which I'm precisely interested in, then I mean I would say nothing. Okay, so here's my functional F, and I recall that I'm restricting myself to F of G, to a hypersurface Fg is equal to 0. Okay. So now I'm trying to compute the second derivative of the stretch. Now for that, I need to have a sort of interpretation of this F of G. And what is this interpretation? Well, it's the following. This F of G, so it's a real number, and it can actually be interpreted as the leading eigenvalue of a differential operator. And this differential operator is minus xg0 plus ag minus 1. Now, if you know a bit, say, elliptic theory or microlocal analysis, then you probably know that it's very difficult to define a spectrum for this sort of operator. And it's mainly because these operators are not elliptic. So it's an operator which has very different properties from, say, the Laplacian, for instance. When you have the Laplacian, you know that you make the Laplacian act on H2, and you're going to be able to define a spectrum and to study very precisely this spectrum. Here, for this kind of operators, it's much more difficult, and this operator is not elliptic. It's actually more, it has a sort of hyperbolic nature. So to be able to define a spectrum and to interpret this Fg as a leading eigenvalue, I need to say a bit how we do this. And what is important to understand is how the geodesic flow acts on distributions. So your geodesic flow, say you're in negative curvature, is going to be Anosov. And when you start with a probability distribution here, say a smooth function, for instance, a bump function or something like this, and you move it by the flow, the fact that it's Anosov, so it's hyperbolic, it means that it's going to be stretched in a direction, which is called the stable direction, and it's going to be squeezed in another direction. So in the end, if you start with a very round probability distribution and you let the time go to plus infinity, then you're going to see something stretch in this direction. And then since your manifold has topology, of course, this line, at some point, they're going to come back here, etc. And what you get in the end is something, if you let the time go to plus infinity, is a probability distribution that has a very strong geometric structure in layers like this. And what you can observe is that the layers are parallel to the unstable direction. In other words, this probability distribution is very irregular in the stable direction, so in the blue direction there, and very regular in the red direction. So that's what we call an anisotropic distribution. And what you can prove is that you can define Hilbert spaces of distributions, which are called anisotropic Sobolev spaces. And so I will denote these spaces by HS and then subscript AN for anisotropic. And you can show that the unbounded operator xg0, so the derivative in the direction of the geodesic vector field, the unbounded operator acting on this anisotropic space of distribution has discrete spectrum in a spectral window, which is real part of lambda bigger than minus a constant time s. In other words, what you get is a sort of family of Hilbert spaces, which is indexed by a parameter s, a real parameter. And as you increase your parameter s, it's a regularity parameter, you sort of reveal more and more spectrum, and it's a kind of a sort of curtain that you unfold, and as you increase S, this red curtain here is moved to the left, and at some point you uncover all the spectrum of your operator. And what you can show is that the f of g that I was giving before, so the pressure of a certain potential, is actually the leading eigenvalue of my operator minus x g0 plus ag minus 1. So there, I mean, this spectrum is really important in Azof dynamics. And for instance, you can show that, I don't know, like for instance, the existence of what's called a spectral gap, namely a gap between the first leading eigenvalue and the second ones. This spectral gap imply the exponential mixing for the flow with respect to Gibbs states, things like this. So this spectral description is very important and is highly related to the dynamics of the flow. All right, so f of g, the pressure of a certain potential, is the leading eigenvalue of my operator here. Yeah, and I forgot to say that these eigenvalues, they are called Polycott-Ruel resonances. And this description in terms of microlocal analysis is mainly due to Foer and Drostrand and Dyatlov and Zworsky. All right. So now that you have a spectral description, it's quite nice because we can apply all the tools from spectral theory. And in particular, in spectral theory, when you have an operator which has like a simple, isolated leading eigenvalue, it's very easy to compute the differential of, the derivatives of this leading eigenvalue with respect to any parameter. So in particular, here we can compute the derivatives of f of g with respect to the metric g. Now, of course, we're restricting ourselves to the hypersurface f of g is equal to 0 so that's our normalization condition. So if we compute the second derivative of f of g, well, we find that it's equal to 0. And after some non-trivial computations, what we can show is that this second derivative is actually equal to the variance of the symmetric 2 tensor H minus, and that's where it's interesting, minus the second derivative of the geodesic stretch. Okay, so what is the variance of a tensor? So it's just, as I said before, when I have my tensor, I pull it back on the unit tangent bundle. So it's really like a function that lives on the unit tangent bundle. And the variance of a function, it's defined by this quantity. So the variance is always, so it's always computed with respect to a given flow and a given measure. And here I'm computing this with respect to the geodesic flow of G0 and the Liouville measure of G0. Okay, and it's given in terms of this sort of horrible expression there. Okay, so now what I get here is that the second derivative of the geodesic stretch is nothing but the variance of the symmetric 2 tensor H. And you can already see from this computation, because there is a square here, that this is a non-negative number. Of course, we're trying to prove that the geodesic stretch is a strictly convex functional. So non-negativity is not sufficient. We're going to have to prove something more. But it's a first clue that says that we might be on the good way. So just a comment here: how do we do to compute when we have an isolated eigenvalue? How do we do to compute its derivatives? Well, it's just some arguments from complex analysis. You write the leading eigenvalue as the trace of the operator acting on the spectral projector, and the spectral projector is given in terms of a contour integral there, and then you have an explicit expression in terms of the metric g. So you can always you compute everything, and that's how you get this result in the end. Okay. So what do we know? We know that the stretch has a critical point at G0, and we know that we have an expression for its second derivative, and we know that its second derivative is non-negative. So we're trying to prove that it's strictly positive. All right. So what we show then, and that's where microlocal analysis comes into play. We show that this variance can actually be written in terms of a quadratic form involving an operator pi2. And this operator pi2 has the property that it's a pseudo-differential operator of order -1. So that's a theorem that is basically it's due to Colin in a paper in 2017, and then we refined the results in other papers. So we show that the operator pi2 is a pseudo-differential operator of order -1, and its fundamental property is that it's elliptic and invertible on solenoidal tensors, which are precisely the tensors that we are interested in. And by microlocal arguments, this automatically implies that it satisfies a lower, you get for free a lower bound for this quadratic form. Namely, if you look at pi2 of h against h, you integrate with respect to the L2 scalar product, then this is going to be bigger than h in the h minus 1/2 norm, and that's where the h minus 1/2 norm of my initial theorem appears, and then to the square, okay, because it's a quadratic term, so I have a square here. And it holds for any tensor symmetric to tensor h that is solenoidal. So in other words, if I look at the geodesic stretch functional that I restrict to solenoidal tensors, then I really get what I was looking for. Namely, I have a function that has a first differential that vanishes at g0, and then its second derivative is strictly positive. And now I claim that this is sufficient to conclude. So just to comment, because it might be a bit strange, how is this operator pi2 defined? Well, what we know, since we have a spectrum, is that we also have a meromorphic family of operators, which are called the resolvent family. Namely, these are all the operators of the form x plus lambda to the -1. So it's a meromorphic family of operator, which it depends meromorphically on the spectral parameter lambda, and it takes values in your anisotropic solveless spaces of distributions. So it's meromorphic, and it has a Laurent expansion near lambda is equal to 0. So you can compute this Laurent expansion. And what we do is we take the holomorphic, so it has a pole at lambda equals 0, and we take the holomorphic part of the Laurent expansion. And we define pi2 as my pullback operator pi2 star. Then I take the holomorphic term, and then I push forward by taking the adjoint of my pi2 star operator. And so that defines an operator, pseudo-differential operators acting on symmetric two tensors on the manifold. Now, this might look a bit strange, and I mean, it's not really clear what it does, but actually this operator R, if you forget about the fact that there is a pole at lambda is equal to 0, so you just say you can take the value of this at lambda equal to 0, then R is nothing but x to the -1, okay? So if you think of x as an operator that is just, you take a function and you differentiate it in the x direction, then x minus 1 would be just the integral of your function along the flow lines. And that's precisely what it does. So R of f, at least formally, you can define it as, well, the integral of your function along the flow lines. But of course, it has to be understood in the sense of distributions, because if you take a flow line for the geodesic flow, then let's say, like an arbitrary flow line, then it's going to be dense in the unit tangent bundle. So this expression, you have no hope to make it converge. So the only way you can make it converge is using the theory of distributions. And that's actually what we do here. All right, so that's the way our operator pi2 is defined, and that's a pseudo-differential operator of order -1. All right, so now that we have this, and we know that the geodesic stretch is a strictly convex functional, we can conclude. So remember that we're trying to prove this. We're trying to prove that, the fact that if you fix a metric G0, you take a metric in the neighborhood of G0, then I can bound the distance between the isometry classes of G and G0 by something involving the limb sup of the ratio of the Markland spectrum. Okay, so I need to go back to this picture. I start with my metric of reference G0. I pick an arbitrary metric G in a neighborhood of G0. And I know that I can always pull back this metric by a first diffeomorphism so that at some point it intersects the blue set here, which is the set of solenoidal tensors. So that's what's called a solenoidal reduction, the first gauge reduction. You can always assume, if you write G prime is equal to phi star of G, you can always assume that G prime is actually a metric on this set of solenoidal tensors. Now what we do is we Taylor expand the geodesic stretch. So we Taylor expand, we look at I of G prime, and we look at the Taylor expansion at the point G0. Now, the first term of the Taylor expansion is, well, the value of the stretch at G0, so it's equal to 1. Then we get the derivative of the stretch at G0, and we prove that this vanishes, so it's equal to 0. And then we get the second derivative of the stretch at G0. So we prove that this term is actually equal to the variance of G prime minus G0. And then we get a cubic term because this stretch functional is at least C3. So we get a cubic term here. Okay, now what I'm going to do is I'm going to put, so the terms here on the right hand side, I'm going to pass them all on the left hand side except this variance term here. So everything moves on the left hand side. What I get then, so it's here, is that the second derivative of the stretch is controlled by I of G minus 1, so the stretch minus 1, plus a cubic term. Now I know that the second derivative of the stretch is equal to the variance of my two tensor G prime minus G0. And I know that my variance can be expressed in terms of this pi2 pseudo-differential operator. And I know that this operator has good analytic properties, and in particular, I have a lower bound for this bracket here. So I can bound this from below by G prime minus G0 in H minus 1/2 to the square. So what I get in the end is that this term here is bounded by the stretch minus 1 plus a cubic term. Now I'm almost done. What I want to do is get rid of this cubic term. And what I can do, and that's where my assumptions come into play, is that I can always interpolate C5 between H minus 1/2 and the space of very high irregularity. Namely, this norm here can, to the power 3, can be bounded by G prime minus G0 in some Cn for a very large n, and then by times G prime minus G0 to the square in H minus 1/2. And I assume that this term here is small enough. So it's smaller than epsilon, and I take epsilon smaller enough. Then what I get is that this term is less than epsilon times G prime minus G0 to the square H minus 1/2, which is precisely the term that I have on the left-hand side. And then what you can do now is that you can swallow this term, which was on the right-hand side, you can swallow it here on the left-hand side. And then by just, this very elementary interpolation argument, what you get in the end is that G prime minus G0, namely phi star of G minus G0, to the square in H minus 1/2 is controlled by the geodesic stretch minus 1, namely the integral of AG minus 1 with respect to the Liouville measure. Okay, so now I'm almost done. Remember that I'm trying to prove this, and for the moment I don't have this, I only have the integral of AG minus 1. Now how do I conclude? Well, for that, I consider a sequence of measures which are supported in closed geodesics and which equidistribute to the Liouville measure. Namely, I'm taking Dirac masses which are concentrated in closed geodesics for G0, and such that the Dirac measures supported in these geodesics converge in the weak star topology to the Liouville measure of G0. And then what I get is that sort of by construction, the stretch, so the integral of AG with respect to the Liouville measure is equal to, well, the limit with respect to J of this quantity. And this quantity is by definition 1 over LG0 of CG, so of CJ, sorry. So that's the length of the geodesic, the G0 geodesic, sorry. And then integral of AG. And as I said before, the integral of AG along a G0 geodesic is nothing but LG of CG, namely when you have your first geodesic for G0, that's the length of the other geodesic for the metric G. Okay, so we start with G0, and then we're moving this geodesic because we're changing the metric. Okay, so then, well, what you get is that the distance between isometry classes is controlled by the stretch -1, and using this expression here, you get the limit of the ratio of the two Martin spectrum -1. And the fact that the theorem here is a bit different than what I get here comes from the fact that I cheated a bit and I restricted myself to a hypersurface. So I restricted myself to f of g is equal to 0. Now, if you don't do this, there's a sort of transverse direction you have to take into account. And that's where you get these sort of extra terms. But the global strategy is exactly the same. Okay, so how much time do I have? Like 15 minutes or something?
You've got about 10 minutes.
10 minutes, perfect. All right, so these were the main things I wanted to talk about, and now things are going to get more, say, conjectural. So I'm going to talk about the pressure metric that we introduced in the paper. So as I said before, this quadratic form, this pi2 of h against h with respect to the L2 scalar product, has a lower bound. So when you restrict yourself to solenoidal tensor. So, so this is very interesting. And what does it say? Because remember that solenoidal tensors are a local representation for isometric classes. What does it say? Well, it says that this quadratic form G here descends as a metric on the moduli space of isometric classes, namely the set of all metrics on your manifold that you quotient by the action of the group of diffeomorphisms. So this here, this quadratic form here descends as a metric on the space of isometric classes. But of course, it's getting a bit complicated because isometric classes, if you take all the metrics which can have negative curvature, say on your manifold, then it becomes a space of infinite dimension. So it's a Riemannian metric, but on an infinite dimensional space. But what is very important, and that's what we found in the paper, is that if you consider the case where M is a surface of genus greater than 2 and oriented, and you restrict the metric G to Teichmüller space, namely hyperbolic metrics that you quotient by the action of the group of diffeomorphisms, then this metric G is actually equal to the Weil-Petersson metric that is well studied by well, people in geometry. So that's I mean that's quite remarkable, because you get an object that is defined in a sort of you know, infinite dimensional space, and when you restrict it to a very particular space, which is Teichmüller space, then you recover something which is very well known to geometers. And here, I mean, we don't really do much here, because the link is actually based on a paper by. So that's on the next slide. Oops, that's on the next slide. The link is made by a paper so it's by Bridgman, Canary, Labouri, Sambarino, where they sort of link this notion of pressure metrics with what's called intersection numbers, and intersection numbers are highly connected to geodesic stretch. So it's a sort of, I mean, the fact that it's that in the end we get the Weil-Petersson metric is a sort of natural consequence of our formalism and their formalism. Okay, now there are plenty of natural questions, because we have a space which is infinite dimensional and it's equipped with a metric. So, well, we can study the geometry of this space. For instance, can one define geodesics, which is not an obvious question, because it's, I mean, the equation for geodesics is now, it's a PDE, so it's something that is quite hard to handle. You can also wonder, what is the curvature of this space? For instance, it's known that the curvature of Teichmüller space with respect to the Weil-Petersson metric is negative. Then is it still true for this infinite dimensional space? I mean, there are plenty of open questions, and we have not really looked at these questions so far. We didn't really have time. All right. So, I mean, everything here is very conjectural for the moment. The second thing I wanted to talk about is called the Thurston's distance. And it's also linked with the Teichmüller theory, as we're going to see. And for that, I need to restrict myself to the set of metrics E, so the set of metrics with topological entropy equal to 1. So I'm looking at the space, the modular space of isometric classes of metrics which have topological entropy equal to 1. And we define what's called the Thurston's distance between two metrics or two isometric classes, which is the lim sup of the log of the ratio of the two marked length spectrum. And now on Teichmüller space, when M is a surface, Thurston actually shows that this is indeed a distance between the two isometry classes, and he even shows that this distance is actually linked to the quasi-conformality of the two metrics. Namely, this distance is actually equal to the infimum of the Lipschitz constant of diffeomorphisms when you pass from one surface to another. So he has like a very explicit expression for this. And what we show in our paper is that...
This distance is asymmetric, no? This distance is asymmetric, no?
Yeah, it's an asymmetric distance. Yeah, you're right. Yeah. And he also shows that this distance is actually generated by a Finsler, an asymmetric Finsler norm. So it's not a Riemannian norm, it's a Finsler norm, and it's not even symmetric. But I mean, it's the fact that it's not symmetric is not very important because you can sort of always symmetrize the thing. But I don't know, he says Thurston doesn't care about this, so he says I don't symmetrize things. But it's asymmetric, yeah, as you say. And what we show in our paper is that this Thurston's distance that we define for all isometric classes, regardless of the curvature or the dimension or whatever. Well, I mean, the curvature still has to be negative, but still, we show that this Thurston's distance is indeed a distance in the neighborhood of the diagonal in the moduli space of isometric classes of metrics with topological entropy equal to 1. Now, well, there are plenty of natural questions, and once again, one can wonder whether this is a global distance, just as in the case of Teichmüller space. But of course, this is more or less equivalent to the marked length spectrum conjecture, so it's probably a very, very difficult question. And you can also ask whether there is a similar expression involving Lipschitz constants, just as for Teichmüller space. All right, so to conclude, I mean, just a very brief conclusion about these two last points. We have new tools available that come from microlocal analysis and which allow us to define sort of geometric notions to study the moduli space of isometry classes. But of course, everything is very conjectural for the moment, so there are no results about this. And we hope that maybe at some point this could play a role in the proof of the global rigidity of the marked length spectrum conjecture, namely the Burns and Kattow conjecture. All right, so I think I will stop here because I'm running out of time. And then okay, I'm not going to talk about this. Thank you for your attention.
Wonderful, thank you very much, Thibault. So could everybody please unmute the speaker? Right, so I'm going to briefly mute everybody again. Firstly, well, thank you, Thibault, for an intense and fascinating talk. Before I ask if anybody else have any questions, I actually have a little question myself. I got just a little bit lost. I wasn't quite sure at which point your function big F enters into the story, at which point that function is defined. Would you mind going over that just again, please?
You muted Thibault.
Ah, yes.
Graham, don't mute the...
Can you hear me?
Yes, now I can.
Yeah, okay, perfect. Yeah, so I was a bit maybe I went too fast about this. So this function f
right.
comes into play at two steps.
But where
First of all,
start?
So oops, sorry, I'm going too fast. Where is f? It's here. Okay, so here's yeah, that's where I say that I'm restricting myself to f of g is equal to 0.
Right.
It appears at two steps. The first step is when I compute the first derivative of the stretch, because I'm claiming that the geodesic stretch functional is a strictly convex functional on the moduli space of isometric classes. So I'm actually cheating because it's not true. It's only true if I sort of get rid of a natural direction which sort of corresponds to the dilatation of your metric. Okay.
Ah, right,
so,
which isn't a diffeomorphism, but...
Yeah. So the thing is that if I really want to get, I mean, I did this for the sake of simplicity. If I really want to get like a really nice strictly convex functional, I have to restrict myself to a hypersurface.
Right.
And so it comes into play at two steps. First of all, here.
And this is where it's defined.
Yeah.
Right.
Yeah, that's where it's defined. Sorry. Yeah.
Yeah.
If I don't assume that I'm on this hypersurface f of g is equal to 0, then the differential of the stretch is not equal to 0. Actually, it's
Right.
it's actually equal to well, to the integral of by 2 star of h, and there's no, if I don't restrict myself to f of g is equal to 0, there's no reason that this is equal to 0. I mean, this would simply be the variation of the volume, and I mean, as I said, if you consider dilatations of your metric, well, the volume varies if you do this.
Indeed, indeed.
So it comes here, and then also for the second derivative. Otherwise, you have an extra term, but you know, it's just it's technical. It's not a very.
So what is the, now I'm not an dynamicist, so what is this unstable Jacobian?
Well, it's how can I put this? It would be the, yeah, I don't have a pen, so I can't write, but it's the determinant of the differential of the flow that you restrict to the unstable bundle.
Ah, right. Okay. So
it has a, it's also called the geometric potential, and the thing is that, so how can I put this? When you study Anosov dynamics, you have measures which are called Gibbs states, which are naturally associated to these flows. And so these measures are given by potential. Namely, when you take a potential and a flow, this gives you a Gibbs state. Now we're studying the Liouville measure, and the Liouville measure is associated to a potential, which is precisely this unstable Jacobian, which is also called the geometric potential. So that's why it comes into play. That's why we have to put this potential here.
Okay. Just one final comment or question before passing to other people. There seems to me to be a very strong parallels between what you're doing here and paper I read, Francois will be able to correct me here, by Bonsanti, Mondello and Schlenker, where you use convex functions to prove the unique existence of certain types of isometric embeddings. And I think this is also related in a way to the construction of Ritschane of harmonic maps between surfaces. Again, it's the same thing. You take functionals over a space of metrics. You look at the Hessian matrix of this functional, and you show that it's strictly convex. It's the same idea. There's the same idea going on there. Francois, you know more about this paper than I do. Can you say something?
Yeah, no, I don't think so, because you're saying that you use convex functional, but I think that's, you know, just saying like that, it's too vague.
Yes, yes. But there's this business in these papers of taking the convex functional, calculating the Hessians, showing that the Hessian is equal to the Weil-Petersen metric. I mean, it's, there are interesting parallels, I think.
Yeah, but here it's any dimension, isn't it?
No, for sure, for sure. Here it's arbitrary dimension. So
what is not clear for me is how you wrote the Weil-Petersen metric at the end. It looks similar as the usual way the Weil-Petersen metric is written, using the L2 scalar product and this divergence-free tensors.
Yeah. Sorry, what is the question exactly?
Yeah, one of the last theorem you cite, and you say that when what you did is restricted to the hyperbolic, to the Teichmüller space, you recover the Weil-Petersen metric.
Yeah.
But is it not straightforward that it's exactly the same? Okay.
Yeah. Okay. It's probably straightforward to the experts, but I was not an expert of this, so but it's indeed straight. I mean, there is an expression of the, well, you you know this, I guess. I mean, the expression, there is an expression of the Weyl-Peterson metric in terms of the second derivative of a ratio of intersection numbers or something like this. And I mean, this is precisely what we're using here.
Right.
And so there's nothing new. I mean, you're completely right. There's nothing new here.
The interest is that it's something valid in any dimension.
Yeah,
no?
exactly. Yeah, yeah.
This nice,
yeah.
this nice generalization.
Yeah, exactly.
Yes, yes.
So,
And do you have some ideas on how to globalize your local results? What kind of geometric tools would you use? Because it seems very powerful locally.
Yeah, I agree. So one thing was, I mean, so there are plenty of open questions related to this, and one thing was whether the geodesic stretch. So we showed that it's locally it's a convex functional, namely in the neighborhood of G0. But one question could be: is it a global convex functional? And if it's a global convex functional, then this should imply the Mark-Lane spectrum conjecture. So it's probably a hard question, but that's something that I remember that we tried at some point to look at this, and then we couldn't figure out really what was going on.
but the space of metrics, the space of all metrics quotiented by diffeomorphisms, it doesn't really have a nice manifold structure, does it? I don't think it is.
If you quotient by diffeomorphisms which are isotopic to the identity, it does.
Oh,
I think
right,
it's
okay.
like a nice Frechet manifold. Of course, if you take all the diffeomorphisms, then it's going to be like an orbifold or whatever.
Yeah.
I mean, that's exactly what happens if you restrict for surfaces, if you restrict to hyperbolic metrics. Yeah, the fact that it's that you're only taking diffeomorphisms that are isotopic to the identity, you know, it gives you a nice structure of a nice manifold. Yeah.
Right. Okay. Are there any other questions?
So you are also interested in studying the geometry of your space of infinite dimensional matrix, space that you with this quadratic form.
Yeah. I mean, it's completely conjectural, so I don't know, but yes, indeed.
And you have some kind of a flow like the Weyl-Peterson geodesic flow and stuff like this.
I don't know, because I mean, we don't even know if there are geodesics. I mean, there should be, but it's not you know, it's not something obvious because you're in an infinite dimensional space. So as I was saying, the geodesic equation is something like, you know, it's a PDE, so it's no longer an ODE. So you have to do things. But I was talking with Daniel Moncler, which seems to be working on related questions, and he told me that usually what is crucial to prove that there are geodesics is a lower bound on the metric itself. So that's precisely the lower bound on this quadratic form, the fact that it's bounded by that it bounds from below h squared in the h minus 1/2. This should allow us to prove the existence of geodesics.
This is nice. Yes. Okay.
But I mean, I don't know. I so far I haven't had time to look at this more carefully. But it's so there was another nice. there was another interesting question which was asked by Gilles Courtois, which is well, is Teichmüller space a totally geodesic subspace of well, this modular space of all isometric classes with respect to this metric? Once again, I mean, I have no idea. No, you know, I don't know. I don't know what to expect actually. So.
Cool.
Okay.
Well, if there aren't any other questions, I guess we should thank Thibault again. So please unmute your microphones. And...
Thank you very much, Thibault. Very nice talk.
Thank you.
Well, I will stop the recording.